Hi everyone. So today we're going to be talking about another way to determine whether a function has local maxima or local minima. So remember this word extrema here. This is basically just a way of grouping together local maxima and local minima into one word. So that's what that word means. So yesterday we talked about how you can figure out whether your function has local maxima and local minima by first finding the critical numbers and then kind of looking at what's going on with the graph before and after those critical numbers. So basically checking whether your function is changing from increasing to decreasing or decreasing to increasing. So I want to write that down again, what we talked about yesterday, and that's actually called the first derivative test. So the first derivative test says that if f prime of c is equal to 0 or undefined, and so I'm going to kind of break this into a few different possibilities. So if you find that your derivative changes from positive to negative, at x is equal to c. So if the derivative changes from positive to negative, the first derivative, that means your function is changing from increasing to decreasing. And so if you just think about what that shape looks like, that means there's going to be like a hill type shape, right? So that is a local maximum. Then f of x has a local maximum at x is equal to c. And then similarly, if your derivative changes from negative to positive at x is equal to c, then that tells you that your graph is going down and then it's going up. And so that means that it has a local minimum. And then if neither of those things happen, so if it doesn't change, if it just is increasing and then it keeps increasing, or it's decreasing and it keeps decreasing, that means that there is not a local maximum or a local minimum. So just to remind you what that looks like in the graph. So this would be an example of a function. We've done this one a few times now, where you have a local max here. And so why is that a local max? Well, the tangent line would be 0 at that point. The derivative would be positive leading up to that point because the graph is increasing. Then the derivative would be negative because the graph is decreasing. So positive to negative means local max. And then here we have decreasing and then increasing. And so that tells us that we're going to have a local min. So now we're going to see how we can determine whether you have local maxima or minima actually using the second derivative. So the reason that, that we're going over this is basically that in some situations, so if you're doing something like what we did, my bad, sorry about that, that's behind the scenes. So if you're doing something like what we did yesterday, where you're actually trying to sketch the graph and you kind of want all this different information, well, then it makes sense to use the first derivative test because you're like already kind of writing down that information, right? If you're already making a table with increasing and decreasing, that's kind of handing you the information about local maxima or minima. But there might be a situation where you don't want to sketch the graph, you don't want all this detail, you just want to quickly figure out whether something's a local max or a local min. And so that's where you would maybe want to try to use the second derivative test. So the second derivative test, we'll see that it uses both the first and second derivative, but the reason it's called the second derivative test is basically this part, the part where you're kind of figuring out whether it's a local max or a local min, that part is going to use the second derivative. So the first part of the second derivative test, just like with the previous example, it has to be true, first of all, that the first derivative is equal to 0. And with the second derivative test, it actually doesn't work if the first derivative is undefined. So with the first derivative test, if you had something that was like, a graph that maybe had a shape like this, you would find that the derivative was undefined at that point, right? But you could then still figure out that, okay, the graph is decreasing and then increasing. If you were dealing with a graph that looked like this and you tried to use the second derivative test, you actually wouldn't be able to use it. So that's not really going to come up too much, but you should just know that the second derivative test you can really only use if you know that the first derivative is equal to 0 at a point, not undefined. So two possibilities. So if the first derivative at a number is equal to 0 and the second derivative at that same number is positive. So let's think about what that tells you. So if the second derivative is positive, what does that mean about the shape of the graph? So the second derivative being positive means concave up, right? So if you have a place where the graph is concave up, so just maybe draw, what does that shape look like? It looks like a U or something, right? Concave up. And then you also know that there's a horizontal tangent line. Well, that tells you it has to be a local min. So let me write that down and I'll sketch like a little picture. So just think about concavity. So if you have a graph that is concave up, and additionally, there's a horizontal tangent line at a particular point, that just, because of the shape of the graph, that kind of guarantees that you're going to have a local min. And then similarly, if you know that there's a horizontal tangent line and then you take the second derivative and it's negative, well, then that means your graph is concave down. And if you just draw a shape of, what does it look like when a graph's concave down? Well, that means that you would have a local max. So, it might be a little like, you think positive would be max and negative would be min, but just think about concavity. Concave up means like a valley and concave down means a hill. So there is a local max at x is equal to c. And then if you take the second derivative and you get 0, basically that just means that it's inconclusive. So you actually, if that ever happens, that tells you that you can't really use the second derivative test and you have to use the first derivative test instead. So the first derivative test is basically, it works in more situations, but it's slower. And the second derivative test is nice and quick and easy, but there might be some situations where it doesn't work. So as I mentioned earlier, places where the second derivative test doesn't work is if you have a critical number where the first derivative is undefined rather than being equal to 0. And then also if this happens, so if you find the second derivative is equal to 0, then instead of doing the second derivative test, you need to make a table and compare like we did in yesterday's video. So let's just kind of verify that all that makes sense with this picture. So again, we had a local max here. And if you go back to the video from a couple days ago when we were talking about concavity, we said that this whole first part of the graph here was concave down, right? And so we have a graph that's concave down, and then we have a place where it flattens out, and so that gives us a local max. And then here we have a part of the graph that we saw a couple times ago. We saw that this was concave up. And so if you have a graph that is concave up, and you have a place where there's a horizontal tangent line, well, that tells you that it's a local min. Okay, so I just want to do a few examples of this. This is probably going to be kind of a shorter video, and I think I forgot to make some new pages here. So let me just throw those in here. Okay. So we're not going to be doing like the whole kind of thing that we did in yesterday's video. We're just going to be finding the local maxima and minima for each of these functions. So we're going to find all local extrema. So again, that word extrema is just local maxima and minima of the function f of x is equal to negative 2x cubed plus 3x squared plus 1. So same as before, we want to start by taking the first derivative, because in order to apply the second derivative test, you need to first know that the first derivative equals 0. So the first derivative is going to be negative 6x squared plus 6x, and that's it. So we want to set that equal to 0. And we can divide everything by 6, just make our lives a little easier. And then we want to factor. We want to see what can we factor out from each of these parts. So we can factor out x from both of them. And if we do that, we're left with negative x plus 1. And so that tells us that either x is equal to 0 or negative x plus 1 is equal to 0. And negative x plus 1 is equal to 0 is the same as x is equal to 1. Okay, so those are our two potential local maxima and minima. And so how do we figure out whether they're local maxima or minima? All we have to do is take the second derivative and plug them into that second derivative. So first we need to take the second derivative. So f double prime of x is going to be equal to negative 12x plus 6. And so we want to plug in 0, first of all. So if we plug in 0, we get 6. And 6 is positive. And so that tells us that we have a local, so let's think about this. Positive second derivative means concave up. And so that means local min. It gives us that valley kind of shape. So that means we have a local min at x is equal to 0. And then if we plug in our other number 1 here, now we get negative 12 plus 6, which is negative 6, and that is negative. And so if the second derivative is negative, that tells us that the graph is concave down, and so that means we have a local max. Local max at x is equal to 1. So let's look at the graph of this to confirm that. So here's the function, and let me just make this a little darker. So we can see that we have, like we said, a local min at x is equal to 0 and a local max at x is equal to 1. Okay, so we're going to do a couple more examples. So let's again find all local extrema. And I guess we didn't, so we didn't find the y coordinates. And if this was on like a quiz or test, I would be clear about what I'm looking for. But yeah, if we wanted to find the y coordinates of these points, we would have to plug them into our original function, right? If we were actually looking for, so like on the graph, the actual local minimum is a y value of 1 at x is equal to 0. And the actual local max is 2 at x is equal to 1. So it just kind of depends on what we're looking for. For the sake of this, we can just say the x value, because really the focus here is on figuring out whether they're local maxima or local minima. So let's do g of x is equal to 3x times e to the x. So this one is kind of like one of the functions we did in the video yesterday, but it's a little different. The other one we had was, I think, 5x squared times e to the x. So again, we want to start by taking the first derivative and setting it equal to 0 to figure out where the potential local maxima and minima are. So derivative, we have to use the product rule. So derivative of 3x is 3 times e to the x. And then we do the derivative of e to the x times 3x. So we get 3x e to the x. So if we want to set this equal to 0, then we can start to factor some stuff out. So we can start by dividing everything by 3. And then we have e to the x plus 3x e to the x. And then we can factor out an e to the x. So we're left with, oops, and I didn't get rid of that 3, right? I divided everything by 3, so that should have been just x e to the x. So if we factor out e to the x, we're left with 1 plus x. And so that tells us that either e to the x is equal to 0 or 1 plus x is equal to 0. And so as we've seen, e to the x is never equal to 0. That doesn't give us any solutions. But here we get x is equal to -1. And so that means that our only possible local max or min is x is equal to -1. And so we're going to need to take the second derivative and plug in -1 in order to figure out whether it's a local max or local min. So we did a derivative similar to this last time. We'll see again. I just think it's kind of interesting to point out that when you take a derivative of something that's kind of like x times e to the x, notice that here's our original function. And actually, when we took the derivative, that same original function popped up as part of it. And so it's kind of this, there's like kind of this pattern of repeating that happens every time you take a derivative. So when we take the derivative of this one, the first part is just 3e to the x, because the 3 just comes along for the ride, and then derivative of e to the x is e to the x. And then we take the derivative of this part, which we already did above, right? So that was 3e to the x plus 3x e to the x. We can simplify this as 6e to the x plus 3x e to the x. All right, so last thing we want to do is now plug in -1, just to determine whether that is going to give us a positive or a negative number. So we get 6e to the -1 plus 3 times -1 times e to the -1. So let's see if we can figure out if this is positive or negative without plugging it into a calculator. So this is going to be 6e to the -1 minus 3e to the -1. So that's going to be 3e to the -1, which is the same as 3 over e. But even without rewriting it like this, we can already tell it's positive, right? Because e to the -1, I mean, e to any power is positive, regardless of what that power is. E to a power can never be negative. And then we just have 3 times something, so that's a positive number. So this is positive. And so that tells us that our graph is concave up. And so that means that we have a local, put it down here, a local min at x is equal to -1. So let's look at that graph as well to confirm that we got it correct. So here's the graph of 3x e to the x. So we can see that there is a local minimum at -1, and that's the only local min or max that the graph has. Okay, so last one is going to be sine of x plus cosine of x. So you actually did an example like this, or you did this example on your worksheet from yesterday. So you maybe already figured out what the answer is, but I just want to do it this way as well. So we're going to, again, find all. And for this one, we're going to focus just on the interval from 0 to 2 pi. So all local extrema on the interval from 0 to 2 pi of the function h of x is equal to sine of x plus cosine of x. Because, when you're solving trig equations, there's going to be infinite solutions, but in order to make our lives simpler, let's just focus on one part of the graph because the graph is going to kind of keep repeating. Okay, so just like with the other stuff, we want to start by taking the derivative. So the derivative is going to be cosine of x minus sine of x. So we want to set that equal to 0. And from here, there's a couple ways that you could solve it. I mean, I think the clearest thing to do is to add sine of x to both sides. And so we get sine of x is equal to cosine of x. So at this point, if you wanted to, you could divide both sides by cosine of x and think of it as being tangent of x is equal to 1. But personally, I actually find it easier to think of it in this form. So what is this asking us? If we're trying to solve sine of x is equal to cosine of x, that's asking us to find the angles where sine and cosine are equal. And so where are sine and cosine equal? Well, one angle that would work would be pi over 4, right? Because at an angle of pi over 4, you have sine is equal to square root of 2, or sorry, cosine is equal to square root of 2 over 2, and sine is also equal to square root of 2 over 2. So one possible solution here is x is equal to pi over 4. And then the other angle where this happens would be at 3 pi over 4. So if you go to an angle of 3 pi over 4, you're going to have negative square root of 2 over 2 and negative square root of 2 over 2. So the other two angles that you might think but that aren't going to work would be 3 pi over 4 and 7 pi over 4. So, and sorry, I wrote this angle down wrong. This is 5 pi over 4. My bad. But those other two angles, 3 pi over 4, so that would be this angle, and 7 pi over 4, those have the x and y coordinates are opposite signs of each other, right? That you have a positive and a negative, and we want them to be completely equal. We want sine of x to be equal to cosine of x. Okay, so x is equal to pi over 4 is one of our answers, and then x is equal to 5 pi over 4. Okay, so now we need to take the second derivative, and we're going to then plug in those numbers into our second derivative to figure out whether we get a positive or negative result. So the second derivative is going to be now negative sine of x minus cosine of x. So if we plug in these values, so let's plug in pi over 4. So h double prime of pi over 4, we're going to get negative sine of pi over 4 minus cosine of pi over 4. So what is sine of pi over 4? Well, it's root 2 over 2, and so it's going to be negative root 2 over 2. And then cosine of pi over 4 is also square root of 2 over 2. And so you don't even really have to finish this off. If you're just trying to figure out whether it's positive or negative, which is all you need to figure out if it's a local max or min, you can already tell it's negative. But if you were to put these together, you would end up with negative square root of 2, because you'd have negative 2 root 2 over 2, which is the same as negative square root of 2. So because this is negative, that tells us that the graph is concave down. And so that tells us that we have a local max at x is equal to pi over 4. And then if we plug in 5 pi over 4, we get negative sine of 5 pi over 4 minus cosine of 5 pi over 4. And so we saw in our picture up here with the unit circle that at an angle of 5 pi over 4, the x and the y coordinates are both negative. So we're going to have negative square root of 2 over 2 minus negative square root of 2 over 2. And so we're going to get two positives. We're going to get square root of 2 over 2 plus square root of 2 over 2, which altogether gives you square root of 2. And so that is a positive number. And so that tells us that our graph is concave up at that point. And if your graph is concave up, that means that you have a local min. So let's look at the graph of this one as well. So here is the graph of sine of x plus cosine of x, and if you click, you can see the actual local maxima and minima. So we have a local max at pi over 4, and we have a local min at 5 pi over 4. And then we get more local maxima and minima as we go, but those are the ones that happen outside of 0 to 2 pi. So this would be, if you took pi over 4 and added 2 pi, that would be like the next local max, and so on. But just between 0 and 2 pi, these are the only two that we have. All right, so that is it for today. So tomorrow we will start looking at some kind of applications of the stuff that we've been doing. So we'll see that finding local maxima and minima can be very valuable, because if you have like a word problem where you're trying to find the maximum or minimum amount of something, if you can translate it into a function, you can use the ideas that we've been using in the last few videos to basically figure out what the maximum or the minimum is. All right, I will see you next time.